Hello everyone, welcome to today's ECA Learning Zone webinar. Today we have Simon Barry from ABB and he'll be taking you through a presentation on life safety transfer switching. This session is being recorded and will be available on ECA's YouTube channel later this week. At the end of the session, Simon will be answering your questions, so please put these in the chat box. Thank you very much for joining, and over to you, Simon.
Thank you, Kat, and thanks to the ECA for giving us the opportunity to deliver this presentation. Yeah, so today's topic is transfer switching equipment with particular reference to life safety applications, and in line with CIBSE requirements, we hope to achieve some learning objectives, which is, as you can see on the screen there, so we learn what a transfer switch is, understanding of the product standards, we take a look at the classifications involved with this area, we look at the different types of transition switching types. Some of the common questions that we get asked is understanding overlapping neutral and bypass, and when and where switches are used in life safety applications. So hopefully by the end of the session we'll have a better understanding of those topics, and to achieve that, this is the agenda. I won't go through all of it, but obviously you can see it's in line with the learning objectives. So to start off with, we'll just take a look at some basic definitions. I guess those of you who are in the electrical industry will know these or have an appreciation of these, but there may be some on the call who may not. So some of the standard definitions and statements that you come across in this topic is primary power source. So this provides power to all loads for an indefinite long time. Then there's the next definition is called the secondary or backup source. So this provides power in case power supplied from the utility is interrupted or differs from nominal values. The transfer switch itself is classified as an electrical switch whose primary function is to switch between the primary and secondary source of electricity. And the major benefits, well, obviously some of these are quite common sense. So consistent power supply if electricity supply from primary source fails, and the ability to monitor and manage the electrical supply to a facility. Obviously, a relevant example of that is the Heathrow incident last week. Yes, so obviously resilient power supply in those situations is a good thing to have, to say the least. So they're the basic definitions. So just to illustrate that, there's a simple animation here. So we have the primary power, which we just talked about, on the left hand side. Then we have the secondary backup power, which in this case is a generator, which is most applications are supplied like that, although we are seeing the use of UPS technologies creeping into the solution as well. So the unit in the middle is the controller. So we have primary power from the DNO. So the controller monitors this and says primary power is healthy, so we can close that switch, and as you can see then the load is energized and everything's healthy. Now we have an interruption now, which in this case is a weather phenomenon. So basically that's knocked out the supplies from the DNO and we've lost power, as you can see, to the load. So the controller now senses that, sends a start signal to the generator. So once the generator is up to speed and the controller deems that the secondary supply is within acceptance of tolerance, it will then disconnect the primary and then supply the load now with the backup power. So that will stay like that now until the primary power is resumed. So again, the controller, we go into the controller a little bit further on, but once the DNO now has restored the power, so the controller now is programmed to sense that. So once the controller is happy, it manages now the reverse switching sequence. So we disconnect the backup power from the generator and we reinstate the primary load to supply the facility. So we're back to where we started, i.e. everything's back up and running as normal. So the last thing that the controller does then is de-energize the backup power. But basically that is the purpose and the functionality of a transfer switch. So as I said, this particular session is geared at more life safety, but the principles, as you can imagine, are exactly the same. So some of the standards that you may need to be aware of around this topic, the main one being the 60947-6-1, which is the low voltage switch gear and control gear. a multifunction equipment, transfer switching equipment. So within this document, as with all these sort of documents, there's loads of standards and definitions. We've just picked out and highlighted some of the basic ones from it. So it states in this document, the automatic transfer switch assembled and tested by the manufacturer either as an open device or mounted in an enclosure. And then he goes on to state other parameters. So the other one there is showing you the voltage levels that this applies to, which is 1000 volts AC or 1500 volts DC. So that's the main standard, but within that standard then it refers to other standards. So an example of that is the product standards. So in this case, it's the 60947 part 3 for switches and disconnectors, fuse combination units and accessories, again in compliance with 1000 volts AC or 1500 volts DC. So this basically ensures that when a manufacturer or an assembler is designing switching equipment, that the products, the devices themselves comply to the relevant product standards. So in this case, it could be, this is switches, but that can apply then to contactors and indeed circuit breakers, as we'll show later on. So what it's stating is that all the subcomponents must, within their own right, comply to the relevant standards within the that product range. The other consideration is BS-EN 61439, the low voltage switchgear and control gear assemblies. Now, a lot of people will sort of recognize this in the realms of switchboard design. So as you can see on the right hand side there, we have power switchgear and control gear assembly. So again, the most common aspect of this is in association with LV cubicle switchboards. But it also applies to control gear assemblies. Now, when you're looking at, again, we talk about life safety, so a lot of the transfer switches become in an enclosed assembly, in an enclosure with ancillary components. So, in essence, that unit should also be designed in accordance to 61439 directives, along as with do switchboards. So, it's just, so when you are specifying or purchasing an enclosed ATS, just ensure that it complies to the 61439 because it is a control gear assembly within its own rights. And as you can see there, there's different parts to the 61439 directive, but part 3 as an example is requirement for distribution boards. So it's just not LV switchboards only. It has far-reaching applications as well. So that's just a few of the common standards that we've that apply to the switching standards. So we'll move on now to the classifications as dictated to by the standards. So we'll take a look at the switching devices. So there's 3 methods that you can use for the devices that actually do the switching. So there's circuit breakers classified as CB, switch technology, which is classified as PC, which we'll come on to a bit later, and contactors CC. So we'll take a look at the circuit breakers. So as you can see there now, there's a picture of 2 air circuit breakers. So this is more in line with really upstream power control. So say 2 incomers to an LV switchboard where you want to do some switching from mains to generator, etc., or mains to mains. Again, we'll touch upon some of the more common ones a bit later on. But again, you can use power circuit breakers, ACBs, molded case circuit breakers. So what these give you now, one of the advantages of this is that, as we know, that the actual devices now have inbuilt trip releases. So they have protection built in them, short circuit, overload, and a raft of other protection functions. So there's no need for additional circuit protection because it's integral to the devices, just by the nature of what these products are. So that lends itself now to a wide range of power applications. So depending on the size of circuit breaker and obviously its ratings, you can go from 250 amp up to 6,300 amp. And indeed with molded case circuit breakers up to 1,600 amp. That's a mistake. It should be up to 1,600 amp. Just to clarify, molded case circuit breakers can go up to 3,002 amp, but generally 1,600 amp is the crossover in most general applications where you start looking at air circuit breakers. So this technology lends itself to quite well most of the scenarios really, and the transitions that you may need in ensuring resilience to your network. So that's class CB. Moving on to switch technology now, which is PC. So the unit you can see there now is quite a common unit now with technologies where the switch mechanism is actually inbuilt. So it's a mono block now. So all the switching and the control, the controller is integral now to the unit. Whereas and we still do these, and we still sell products along with other manufacturers where the controller is off board. But this is just an example now of where technology is now with the monoblock embedded compact design. So this allows you to have, again, the common types of switching: open, open delayed, open in phase. One of the advantages of this type of technology is that it has an inbuilt mechanical interlock because of the way it's designed. So the primary and the secondary switch shall never be on at the same time. Whereas when you're using power circuit breakers or contactors, you need to ensure that you incorporate another accessory, i.e. a mechanical interlock accessory, to ensure that you do not have any situations where both switches are on. This type of product, it's inherent in the design. Convenience, we suggest it's convenient because you have manual operation. So units like this, certainly the ABB one you can see there, as a handle. So if for whatever reason, if the unit fails to change over, which could be an error in the control circuits or indeed the unit itself, which is quite rare by the way, but you can actually pull the handle out now, go up to the unit and then swap it over manually, switch from auto into manual and then switch the unit over. So that's quite convenient to do. It's more convenient than when we look at the air circuit breaker situation that we just saw with two pairs of ACBs. Then obviously it can be done, but you need to stop and think a little bit more on the sequence when you need to intervene with manual operation. So again, with switch technologies, as with the power circuit breakers, a good range of power applications because they're available in various current ratings. And again, looking at life safety applications, they're available in enclosed versions. And again, panel builders will use this type of product in a chassis mount situation where they go into a stack of a switchboard maybe as an incomer for switching two supplies into the panel itself. Technology wise, they like with the air circuit breakers and motor case circuit breakers, there's a raft of different protocols now to connect to third-party monitoring systems such as SCADA, BMS, and whatever plant infrastructure the client has. And you also have a degree of advanced features now, such as power measurements and predictive maintenance. So these units come with a degree of basic controller up to more advanced functionality, depending on the nature of the business concerned. So the third one in the switching devices now is contactors. So they're classified as CC. So as you can see with the image on the right-hand side there, so these are more at home really for frequent switching operations, because that's what a contactor is designed to do. It has a longer robustness for high frequency switching. Fast open transition transfer switching is cost effective with solutions at the range roughly up to 250 amp. As we know, a contactor has an inbuilt electromagnetic coil for its operation. And it's a simplified system, really. The only downside with this is that you need more. As you can see, it is like a panel builder solution because there's a lot more components now, as opposed to the integral embedded monoblock unit that we just saw. Now we see these sort of solutions, they're still widely used, but again, as we'll see later on, be careful on product selection, because when it comes to life safety, this will not comply, which we'll explain a bit later on. But certainly in the industry process control, where it's not for life safety, it may be used for switching different supplies to different loads for a raft of different reasons, sort of duty control, etc. So contactors are allowed and they're in the standards, but not for life safety, as we'll find out a bit later on. So we've seen the devices now that actually do the switching. So now we have under the classifications controlling methods. Again, there's three different options here. You have manual, MTS, remote operated switching, RTS, and then the automatic transfer switching, ATS. So the manual operation, it is what it is. That's an example there of a manual switch with the handle on the front. So this normally has 3 positions. Position 1 for on for the primary supply, an indefinite off, and then what I mean by that is that switch will stay off until somebody comes along and moves it again to position 2. And that's what we call an open transition, which we'll take a look at a bit later on. So again, very simple operation. It's operated by maintenance people and personnel, and it's generally a 3-position unit. So then we have remote methods then. So there's various controllers available on the marketplace to actually control the switching. So I've mentioned embedded ATS, as we saw with the 2A circuit breakers that we saw now have, upon the right release selection, embedded ATS functionality. So you can now make those breakers behave like a third-party controller. So what that does now, it negates the need, and maybe could save a bit of space in the panel, because the technology now, because of the speed of the process, is now embedded within the breakers themselves. And again, it lends itself to the common transition types, main, time main, open delayed, etc. We then have dedicated sort of controllers, DIN remote controllers, and again, this is quite popular with the panel builders to control incoming devices to an LV switchboard. So basically, you choose the right one that has the right software in it to suit the application. As you can see on the screen there, there's quite a lot of flexibility there. There are occasions where sometimes the switching combinations and the matrix of switching combinations is too complex for the embedded situation and the externally mounted controller. So then you probably revert to a PLC control, obviously, because the actual limitations is limited by the software, which pretty much is limitless, because you can now program the combinations to any combination that exceed the first 2 options. Excuse me. And the last one then is electronic relays. Certainly we still see applications with this, going back to the contactor control. You might have electronic relays, timers, phase failure, under voltage relays, etc. So these lend themselves to more of a panel builder solution. But again, commonly used, nothing wrong with that. It's just another option depending on the solution required. So that's the 3 methods. The controller, we've talked about the controller on and off for the previous slides, but basically, as we saw with the graphic earlier on, the controller actually manages the process of switching from primary power to the alternative power source, which, like I say on the example, was a generator. It could be another fixed supply, it could be a UPS, it could be a battery energy storage system. But the controller's function is to monitor and control the switching procedure. So essentially, like we saw with the example, it monitors the condition of the primary supply, and if that primary supply falls out of tolerances or you lose it, then it initiates the switching transfer to the backup supply. So as we saw again with the example, when the generator came on, we stayed for a predetermined time, and again you can program the controllers now to be 10 minutes. The time delay or revert back to mains function is governed by what the client requires. I've known some cases where it's been 12 hours or more, and sometimes only once, by the way, it was 24 hours. Now, it obviously depends on the resilience of the supply. There could be areas where the supply, unless it's on for a long time, you don't want to switch back, because you might not you'll be flip-flopping back and forth. So it's user configurable on the switch back time, but all this is controlled by the controller. A lot of them will still have the communications to tell and inform BMS systems, PLC systems. It does all your synchro checks. It may be required to shed non-priority loads. If so, as an example, if your generator is not fully rated, you may need to shed loads so the generator can feed the loads that are only essential. So all that functionality is the job of the controller. So we've looked at the switching device, we looked at the controlling methods available, we talked about some transition types. So some of the three basic ones that we see are open delay transition, open in phase transition, and closed transition. So just to explain what these actually mean, the open delay transition is commonly known as a break before make. So this has three positions. So this is exactly like the manual switch that we saw earlier. So basically there's three positions. Position one, indefinite until somebody comes and switches it over. Off, indefinite, and then position two. So although the one we showed you was a manual one, this could still be an open delay transition with an automatic controller or like a PLC, etc., doing the control. But that basically is what the transition is. It's one indefinite off, position two, and the reverse. The opening phase is similar, except you haven't got that indefinite off. When it switches, it goes from 1 to 2 at a time limited by the mechanical functionality of the mechanical speed of the actual switching device. So typically the integral switch that we saw earlier, the all-in-one mono block, that's typically, certainly with ours, it's roughly about 48 milliseconds at switching transition. So there is no indefinite off. When it switches, it goes from the position 1 to 2 and 2 to 1. So that's commonly what we call a break before make, same as the first one. And then we have what's called then a closed transition. So this is a make before break situation. So what that means is that when you switch from the primary to the secondary load, the actual load itself does not see any break in the supply. It's continually supplied by either supply one or supply two. But there's a moment, obviously, during the switching period where it is being supplied by both loads at the same time. So one of the main things you have to ensure when you're looking at a closed transition is that both loads are synchronized. So again, the job of the controller is to ensure that when you switch from primary to the secondary load, or supply one, supply A to supply B, that they are synchronized, because they will be delivering power to that load together at the same time during the switching cycle. So they're the three common definitions that we frequently come across in power transfer switching. So just to re-emphasize, we're moving on to sort of the life safety aspect now. So there's a typical network there with transformer 1, transformer 2. So when we looked at the air circuit breakers and the motor case circuit breakers, that's generally found at the incomers of the main LV switchboard, and obviously it can apply to MV systems as well. But from the ATS is generally found now nearer the load itself, so the sprinkler pumps, firm extract fans, etc., and all those sort of life safety equipment. The ATS switching now is further down the supply chain and more so in the sub-distribution main, so it's nearer the load that needs to be controlled with the dual supply upon mains loss. Another function within the standards is utilization categories. We see these in specifications from time to time. So just to explain what these are when it comes to transfer switching. So this table shows there's two utilization categories, operation A and operation B. So within there now you see alternating current and direct current. So I think we're all familiar with the AC31. As you can see there, these are classifications of the different types of loads that switches are designed to manage without causing any problems, i.e., short circuits and can withstand faults, etc. Basically, it involves, is it a resistive load, or is it a mixed load, or is it, a high induction load? So these categories explain and classify the different types of loads that you may experience. So when it comes to the transfer switches, as you can see now, there's category A and there's category B. So category A is for frequent use and category B is really for infrequent use. So if you look at the two tables here, the one on the top, if we look at the rated operational current and we look at the 100 to 300 amp range, with category A, these dictate that the switches themselves now are tested. As you can see there, there's two other columns here, without current and with current, but the total switching number is the same. So with the 100 to 300 amp rating, it's tested with 6,000 cycles, giving you a total of 6,000 switching operations. But the same current rating with category B is now without current. So as you can see, if you look at a comparison on that, without current, i.e. offload, it's 5,000 cycles, and with current it's 1,000. But the main figure there is the 6,000 operations is still the same. So the difference really between the two is offload and onload. Now we suggest sometimes when we see specifications come through and they're asking for a category A switch, we do not questions the wrong word, but we do ask, is that what you're really looking for? Because we would say that normally in most general building services, as we explained earlier, when your transfer switch is switching, it's generally offload anyway, which falls in line now with category B. So that's quite important really, because as you can see there on the slide, if you definitely want a category A switch, as you can see now, a switch that's got to switch 6,000 times on load is going to be a bigger and a more expensive solution than the Cat B version. So that's the main difference really between Cat A and Cat B. And again, like I say, generally it's Cat B that we see for life safety, unless there's another reason that you want a Cat A, but that's, like I say, it's more of a higher performing specification unit when you're looking at Cat A for obvious reasons. So another common area of conversations that we have is the neutrals, and obviously more important, switch neutrals or not. So just to run through a few examples there. The first one is, as you can see there, a fixed neutral. So you can see that this particular diagram is showing you the ATS unit in the red box. So we got 3 poles there, but as you can see, the neutral now is not switched. It's a fixed neutral. So if you look at the primary source on the left, and then we got the secondary source on the right, and then we have a load. Now, this is fine. It still obviously switches from primary to secondary when it needs to. But if you look at the neutral path, the earth path now, this is now, because the neutral is not switched, this earth path is shared between the primary and the secondary source. So if you have any earth fault protection, this potentially can affect the functionality of that earth fault protection device. So that's one of the things to be wary of when you're looking at a fixed neutral switch. So then the obvious progression from that then is to have a switched neutral. So now we have a 4th pole with the ATS. So as you can see there now, this is on the primary source, and the neutral now is not shared, it's actually isolated from the secondary. So that eradicates now any potential earth fault detection with your earth fault relays. Obviously, when you switch over, the 3 main poles switch along with the neutral. So you have a break. It does switch the neutral, but you have a break in that neutral path momentarily, dependent on the speed of operation of the switch. So the next progression of that is overlapping neutral. So a quick question: what is an overlapping neutral? Because there's a couple of we see in meetings that there's different answers to this, but basically this refers to the 4th pole of the switch used for switching the neutral conductor operating in a make before break manner. Now we just saw in the transition examples what a make before break manner is. So as we can see, and the other important thing is overlapping neutral is not a solid or a fixed neutral. So this diagram hopefully illustrates what we mean by an overlapping neutral. So again, like we saw with the switch neutral, in this position, when you got the primary source being fed to the load, as you can see, the three phases are being supplied to load along with the neutral. And the neutral now, like with the switch neutral, is not common to both the primary and the secondary. The difference between this one and the switch neutral is that the load never sees a break in the neutral. So that moon shape there is trying to illustrate that when the switch switches over to the secondary source, the poles go over, but that cam effect actually maintains the neutral at all times to the load. So the load does not see a break in the neutral on the way that fourth pole is designed. So what it does, there'll be a moment where the load will see both neutrals, but then it switches permanently then to the secondary source. So the importance of this really, we see overlapping neutrals a requirement where normally you may have some sensitive electronic equipment downstream, which might not like having what we call a floating neutral. So you may have voltage variances which may cause damage to sensitive equipment. So if there is a concern over that, then overlapping neutrals may be the best solution. But basically, this is what it means. So we've looked at the standards, we've looked at the hardware, the different types of hardware available to do the switching. We've looked at the controller methods, and we've looked at some of the common issues now with the neutrals. So again, there's solutions available, which is good. So now with this sort of section of the talk really goes on to the actual life safety side of transfer switching. So we'll take a look now of the applications and standards and the regulations that you need to be wary of. Like with all talks, this is not a deep dive. It's just looking at the more high view basics of what you should be considering when choosing transfer switches for life safety. So just to start off, and again, I'm sure by now we're all aware of the Building Safety Act 2022 that came into force in July 2020, and then obviously went through a couple of amendments there. So the reason we're putting this in, because it does really focus the mind on correct product selection, shall we say, because there's a lot more accountability now since the Building Safety Act has come in. So these are just reference slides that we put in just to just to make you aware that the actual life safety equipment now needs to be the correct specified and correctly installed. So along with that then we saw higher risk buildings coming into the Safety Act. So again, we'll just show an example of what that high risk building means, and then accountable people, persons, safety case reports, and more importantly, the golden thread. So obviously, if we do have a situation where there's been an incident, then now there's a golden thread where product selection, was it right? Why did it fail, etc. There's more accountability now, more than ever, when choosing life safety equipment. So HRB is a common phrase now, high risk building. So the definition of this under the Safety Act is a building of at least 18 meters in height or at least 7 stories high, and which contains at least 2 residential units, including hospitals, care homes, and student accommodation. It doesn't include hotels, prisons, and military accommodation because they're exempt under the HRBs. So I guess it's more aligned really to residential buildings and the like, for obvious reasons. Obviously, with tragedies such as the Grenfell tragedy, as it's highlighted. So again, this is just another extract here on a slide. Like I mentioned, the golden thread, and it does actually say, looking at the right-hand side there, collected by a digital electronic record, which forms a golden thread. Obviously, things like BIM models and the like now assist in that, achieving that. And then we've just highlighted a compliance declaration, a signed statement that the work complies with the building regulations and all relevant duties have been fulfilled. So this is not part of really transfer switching, but it just covers the whole topic of life safety equipment, obviously, which ATSs can have a part to play in that. So it's just re-emphasizing, like I said before, that you really need to ensure that your product selection, like with the standards that we've been through with ATSs, they do comply, and there's no ambiguity of whether they do that or not. So under the life safety systems headings now, there's certain requirements now. So there's, again, this is not a product standard. This is more of an approved code of practice, I guess, management. So BS 9999 and 9991, a code of practice for fire safety in the design, management and use of buildings. So these are documents intended for designers and architects. So basically what they cover is the best practice framework for safety, the design, management and use of buildings to achieve acceptable levels of fire safety for people in and around buildings, and also requires electrical supplies to life safety and firefighting systems backed up by a secondary supply source independent of the primary supply to the building, i.e. an automatically started generator or a secondary supply. So examples that we've seen on previous slides within the talk. Again, like I said, I'm stressed, this is not a product standard, but it's more of an installation management document. This document, however, BS 8519 2020 edition, is one of the main documents now. So this is selection and installation of fire resistant power and control cable systems for life safety, firefighting and other critical applications code of practice. So within this document, certainly with bypass arrangements, it says where occupation of the building is conditional upon the availability of life safety and firefighting equipment, a single or dual bypass arrangement should be provided to enable the changeover device to be maintained without loss of service from the critical plant. So that is saying basically that if you have to do maintenance on your ATS assembly, then you must have a single or dual bypass. So in the event of loss of the primary supply whilst you're doing maintenance, which is a risk obviously, you can still maintain supply to the life safety equipment. So that's achieved by a single bypass. So this comprises a single bypass on the primary supply or a dual bypass, which gives you a bypass option on supply 1 or supply 2. Now, very often we're asked as a manufacturer, do I need a single or dual bypass? And again, you know, it's a risk assessment deemed decision really by the designers and installers. We can just, like with all manufacturers, we can supply you with a single bypass or dual bypass. You know, it's not for us to tell you what the situation is for one or the other. But just to explain on a simple diagram what the single bypass sort of looks like, as mentioned in the standard there, that when you look at a single bypass arrangement, you are then bypassing the ATS and its associated components via the primary supply. So if you're going to do maintenance and you do lose power, then it's a risk assessment really on what are the repercussions and consequences of me being unlucky enough to lose mains whilst I was doing maintenance for half an hour or whatever on that particular unit. If there is a concern, then the dual bypass gives you options obviously of mains 1 or mains 2. So you've got a selection, so you're not limited to just the primary mains. Now, one of the main benefits of that, you could have a situation where you could have a maintenance on your upstream supply. For example, you could have transformer A and transformer B. So if you need to do maintenance on any upstream switchgear, you can then actually switch deliberately as part of a maintenance procedure to mains 1 or mains 2 to give you options, because 1 month you could be running on transformer A, then the next month you could be running on transformer B, not just necessarily losing, you know, a fixed supply and looking at a backup supply. So the dual bypass does give you options on that particular, how you need it to perform under that particular set of circumstances. So this is an image here of happens to be an ABB unit. So as you can see there, this is a dual bypass. So you got the ATS switch changeover unit, which is that monoblock arrangement. You got the ATS switch disconnector, and then you got the changeover switch or bypass, and then the supply one or changeover switch. So that just really shows you what the hardware looks like, looking at those two simplified line diagrams. So going back to BS 8519, we've picked out other extracts within this standard. So looking at the primary and secondary source of power is required for critical life safety plant. This defines now what that secondary source shall be. So it states, be provided independent of the primary supply, typically an automatically started standby generator, exactly similar to the one that we saw at the start of the talk. It does say, however, note, separate independent feeders from a network shall not serve as electrical sources for safety services unless assurance can be attained that the two supplies are unlikely to fail concurrently. So it says there is an exemption to have a fixed supply from another part of the fixed network, but you must have assurance from that supplier that the two are very unlikely to fail at the same time, or you've got another sort of redundancy option as a backup. Now we sometimes see this on big hospital schemes where you've got two MV networks within the utility, and again the chances of both failing, that's a risk assessment done by the designers and the local suppliers. So it then goes on to state that when you do lose primary source, that the switchover starts automatically and will automatically, like we explained with the controller situation, initiate the changeover procedure. And then it says, be managed by an automatic transfer switch ATS in compliance with BS EN 60947-6. So going back to the standard that we went through or touched upon earlier, 8519 does make reference to other standards relevant to transfer switches. It also says the ATS device should conform to BS 60947 Part 6 Part 1, which we just looked at, and should be based on switch technology. Now, we all know that switch technology now is the PC classification rather than circuit breakers or contactors. So I mentioned when we looked at the classification, there's nothing wrong with circuit breakers, nothing wrong with contactors for the job of the application that it's been called upon to perform. But when it comes to life safety, the standard BS 8519 says you cannot use circuit breakers or contactors. It must be a switch technology. Also, it says the ATS should be a single component with integrated controller from the same manufacturer. Now, this does cause conversations from time to time as to what that actually means. So does it mean when we saw the same monoblock, as you can see on the picture on the left there, that ATS, by definition of its construction, the switches are integrated, the control is integrated, the manual operation functions integrated, the comms facilities are all integrated because it's all one unit. But does that make reference then to the other components constituting that solution, i.e. the switches, the bypass switches, the isolators, and all the ancillary products? We say that it does. Others may have a different view, but this is what the 8519 document states. Another document maybe to consider is the BSRIA BG 70/2021, the Life Safety and Firefighting Power Supply 2nd edition. In that document, it sort of, as with all of these things, eradicates any ambiguity as a panel on the best code of practice and the best way to look at this. But in this document, it states that the automatic changeover device should be a single tried and tested component from a single manufacturer, along with the associated controls, indication, and bypass arrangement, where necessary for service availability reasons, as we just mentioned, as a type tested and certified solution. So this guide gives a steer really, and it tries to reduce the ambiguity as to what does it mean when it comes to ancillary equipment. So this document is quite clear that it means the whole assembly must be from a single manufacturer and comprise of single manufacturer's components. So it eradicates any ambiguity as to what that means. So a summary of the standards, we looked at 60947 part 6 part 1. We looked at the product standards, the low voltage switchgear and control assemblies, and then we looked at the ones as discussions for life safety applications, i.e. 9999 and 8519. So some of the applications that we commonly see now obviously is for life safety. So we're looking at exit lights and exit signs, fire pumps and hydrants that we see in building, elevators, smoke extract systems, but it can also be used for process chemical productions, healthcare facilities. So it depends really on whether the risk obviously is life safety, but also it could be a financial cost implications on loss of supply, as we spoke about at the top of the talk really. But yeah, so it has various uses and applications. Some of the market sectors that you find these products in, obviously critical power situations such as hospitals, data centers, infrastructure. Again, looking at recent events with Heathrow, industry, various power plants, and of course commercial and residential buildings, in particular high-rise buildings, where that's where we see like a higher density and a higher number of ATS switches being used in the design. So that brings us to the end of the talk. So in summary, we set out to have to achieve certain objectives. So hopefully we now are a bit more wise on what a transfer switch is. We understanding the product standards. We took a look at the different classifications. We had a walk through the different transition types that you come across in this sort of technology. We talked about overlapping neutral and bypasses, and we took a quick look at the life safety applications and where these products and solutions are used. So that brings us to the end of the talk. Kat, are you there?
Hello, yes. Thank you very much for that. Do we have any questions?
Any questions from the participants?
I haven't got any at the moment, but we will give it a few minutes.
Hello?
Can you hear me? Can you hear me? Hello.
Yeah, I got you now. Yeah, I can hear you now. Yeah.
Yeah, we haven't got any questions at the moment, but we'll just give it a few minutes
to
see if people to drop anything in. Oh, so I've got a question coming. So, for an HRB life safety application and the smoke vent or roof mounted gen set is bonded to the LPS, will external type 1 SPDs be required, or are they built in?
Surge protection devices.
Yes.
Can you read that again, please,
Yep.
Kat? Yeah.
For an HRB life safety application and the smoke vent or roof mounted gen set. So if the smoke vent or roof mounted gen set is bonded to the LPS, will external type 1 SPDs be required, or are they built in?
Oh, now that's a different topic going away from this, really. Now, I don't know if you know that FIRS are now part of ABB. I would say yes. Is there what I need to do, because it's not my field of expertise, really, Kat? Can we take the details of that question? I can pass it on to our surge protection guys.
Yeah, absolutely. We will pick up with you.
I mean, as far as I'm aware, and I've sat in some of the first presentations. Again, there's another CPD on surge protection, but anything that's any bit of kit that's going outside externally that can be subjected to lightning predominantly, then it should have a type 1. But I'll get that confirmed, Kat. Really, yeah. I would like to. But I think that would be the situation, but I'll have to get that verified with our surge protection.
Yeah, no problem. We'll drop you an email on that one.
Okay.
See if anyone else is sending in any questions. It's obviously very thorough and clear if there's not many questions. Yep, so we've got another question come in. Can you clarify that you can't use MCCB on life safety systems now? And would this need to be fuses instead? For instance, within the main switchboard, putting fuses for fire lifts, etc.
We normally obviously see again the designs that we come across and we build panels to. We normally see switch fuses on the live side of the incomer, so they're not forming part of the outgoing circuits when they go off to the sprinkler motor starters and things like that. But again, that's slightly going off the well, it isn't really, but that's not part of this. But generally, we see switch fuses. We very rarely see multi-case circuit breakers.
Okay. Hopefully that answers your question. Any more questions at all? If anyone does have any questions after this session that they think of, you can just speak to your regional manager or get in touch with someone at ECA and we can pick up on those. We've got a few thank yous and thank you for a good presentation. There you go.
I mean, just going back to that the fuse question, it's a good question really, because it does cause sometimes we do get asked that. But as far as I can see, it's all about, like I say, we're not design engineers. We work with design and consultancies predominantly, and again, with designers in the contracting market. But generally, it is fuses. It's all about having run to destruction that you don't want. Although you want to protect that cable as much as you can, you don't want things tripping. Random tripping when you're relying on a pump, a sprinkler pump to keep working as much as it can. So like lock rotor situations and things like that, fuses are deemed more resilient as a protective device, other than multi-case circuit breakers really.
Okay, thank you. Right, I don't think we're going to get any more questions today,
Okay.
but obviously, oh, sorry, no, we've just had one thing. It says, it's the fact we have a lot of designs with MCCB, but generally I prefer fuses due to tripping.
Yeah. Well, I have seen designs with multi-case circuit breakers, and then we got to sort of go through all the tripping curves and make sure that the double check again with the electrical designers that lock rotor situation currents are not affected by the won't be harmful to the multi-case circuit breakers. You've got to sort of specify it the right rating, whereas I think with fuses it more or less eradicate. I mean, you still got to consider that, but fuses are deemed more resilient.
Yeah. Okay. Well, thank you, everyone. We'll leave it there, and thank you very much, Simon.
Okay, thank you,
right,
Cap.
thank you for joining. All right, thanks all. Bye-bye.
Okay. Good afternoon.